One of the most symbolic achievements of humanity is the invention of flying machines, better known as airplanes. From the earliest powered prototypes, like the 14 bis, the idea of soaring into the sky aboard a machine has captivated countless children and adults alike, myself included. Despite having flown numerous times on commercial flights, I still find myself utterly mesmerized every time I step onto a plane. From the moment the aircraft accelerates down the runway, to the feeling of being pressed back into my seat as it tilts upwards, to watching houses and buildings shrink below as we ascend above the clouds, reaching heights I can hardly fathom. Each experience is nothing short of magical. I have a fear of heights, so the natural question that comes to mind is, how do airplanes actually fly? How do these massive metal objects weighing tons lift off the ground and soar beyond the clouds? You might have been taught a simple explanation all your life, but it's likely not the full story. There are 4 key forces in flight: weight, which pulls the airplane towards the earth; lift, which pushes it upward; thrust from the engines, which propels it forward; and drag, which resists its movement through the air. Lift is generated as air flows around the wings, and if the lift force is greater than the airplane's weight, it stays aloft. But this is just a partial answer. What's missing is how this airflow around the wing generates lift, and the answer is simple. No, just kidding, it's not simple at all. If you search online, you'll find numerous explanations of how lift works in airplanes, but most of them simplify things greatly to make the concept easier to understand, often leaving out critical aspects of how airflows actually work, and it's understandable why. Simplifications are necessary to make these concepts more accessible, but in doing so, they slightly obscure the true marvel of human ingenuity in creating airplanes. As researcher Philip Spellert once said, it's easy to explain how a rocket works, but explaining how a wing works takes a rocket scientist, and I am certainly no rocket scientist. But even so, I'll do my best to explain how wings work and why the physics of flight is both so complicated and so incredible. Fair warning, some simplifications will be necessary, but I'll still try to make it clear just how complex the physics of powered flight really is. The first thing we need to understand is that fluid mechanics, which describes things like liquids and gases in motion, is not intuitive. One of the most remarkable properties of fluid mechanics is that it's impossible to separate causes and effects within a flow. The flow acts as a single entity, and all the characteristics of the flow, such as velocity, pressure, and turbulence, at any given point depend on the characteristics of the flow at every other point. It's like trying to isolate a single section of a river to calculate how the water behaves there, without considering the entire river and the forces acting on it. If you want to attempt something like that, you have to make artificial approximations, which can give you useful but not entirely accurate results. Fluid mechanics is so complex that proving whether the field's fundamental equation has a general solution is worth $1 million prize. And yet, despite its complexity, we've managed to build airplanes that can fly. The air in our atmosphere is a fluid. Anything that flows is considered a fluid, and fluids are not limited to liquids. When air moves relative to an object, we have an airflow, and what's crucial for describing flight is the airplane speed relative to the air around it. The high speeds of an airplane are generated by its engines, which create thrust and accelerate the plane to high speeds against the air. Air is made up of countless particles moving randomly in all directions. A significant portion of these air particles will collide with the airplane's wing, and because the wing is rigid, the air around it will change shape according to the wing's form, and these changes will propagate through the air. The wing displaces some of the air around it, which in turn displaces even more air further away. Yes, the effects of the wings propagate outward than just the air in direct contact with them. This deformation of the air creates circulation, altering the pressure, velocity, and direction of the air's movement around the wing. As a result, both the air passing over and under the wing is deflected downward. By pushing the air downward, the air, in turn, pushes the airplane upward. This is Newton's third law of action and reaction in play. Most people learn about how airplanes work up to this point, but that only explains part of the force that keeps a plane in the air, not the whole picture. Beyond just the change in direction, the air passing over the top of the wing moves faster, and as a result, the air pressure decreases. This increase in speed and decrease in pressure is a self-reinforcing cycle. Faster moving air tends to lower pressure, and lower pressure encourages the air to move faster. Meanwhile, the air passing underneath the wing experiences the opposite effect. Its speed decreases and the pressure increases. In essence, the air above the wings ends up with lower pressure than the air beneath the wings. Pressure, after all, is just force distributed over an area. Since the pressure is higher below the wing, there is a force pushing the airplane upward from underneath. This is another part of the lift force that keeps the plane aloft, but it's still not the entire story. The subtle part is that the change in airflow direction and the difference in pressure aren't two separate effects. They form a feedback loop. Changes in the speed and direction of the airflow encourage the formation of different pressure zones, which in turn influence further changes in the speed and direction of the flow. Additionally, variables like the airplane's speed relative to the air, the shape of the wings, and their angle of attack all influence the intensity and direction of the lift force. Because of this, it's possible to maneuver the airplane by adjusting these elements. Planes can change speed using their engines. Wings have movable parts that allow them to alter their shape to change the direction and strength of the lift forces, and with these changes, they can also modify their angle relative to the airflow. It's challenging to fully convey the most incredible aspect of fluid mechanics. Everything in a flow is interconnected. This interconnectedness is what makes the calculations difficult and the explanations complex. Even a basic explanation of flight relies on multiple elements of airflow, such as direction, speed, and pressure. There's nothing simple about aviation. Yet, despite this complexity, we've mastered one of the most challenging areas of physics to create flying machines made of metal, and with them connect the most remote corners of the world. And I never cease to be amazed at just how clever humans are. Thank you, and see you next time.